loved it, and in particular, I'm a proud partner of Siobhan and James, and love the visualization. It just shows the growth and energy that's happening. And we're going to start with some of the applications that are occurring in AI right now. And we have a talented group up here. First on deck is going to be Sabrina Atienza. So she is won hackathons, top 5 in the AngelPad hackathon. Angel Hack, and she's also a Berkeley grad, and you should read her blog. She says apparently we waste $37 billion in meetings a year, and she can help us figure that out. But the thing I think is most special is she's an engineer, and she also has insights into sales. So Sabrina, tell us more about Curious.
Yeah, absolutely. Will I see slides up there? Okay, awesome. So great to meet all of you. My name is Sabrina Atienza. I'm CEO and founder of Curious with a Q. My background, as Karen mentioned, is in computer science and physics from UC Berkeley. So what our company does is we leverage artificial intelligence to help keep your sales team on track. I figured for the first couple slides, I'll share with you the types of conversations we have with our customers. Then the next couple slides, I'll share how we leverage AI specifically in our product to help solve these problems. So to get into the mind of our customer, imagine you're the CEO of a venture-backed company. You've proven product market fit in one vertical, and now you're scaling your sales team to expand to new markets. What if I could show you, as the CEO of that company, how your sales force lost $40 million in growth opportunity last year? It's a big number. So what we mean by this is our biggest insight working with clients is that a leading source of lost growth is due to low-quality conversations between your company's sales team and your company's customers. So, for example, imagine you're that CEO. You have 200 sales reps on your team, each talking to 10 customers per day. Over the course of 200 business days, that's 400,000 conversations with potential customers that your sales team's interacting with. Now assume just 1% of those conversations are deals lost that you could have won. So what I mean by this is in a traditional sales force, you have your A players, B players, C players. Your A players are your top performers. Your C players are your underperformers. In a traditional sales force, if your B and C player is talking to a customer, you may lose that deal not because the customer is not interested, not because the customer is not qualified, but because the conversation they had with your salesperson was low quality. They were not engaged. They were confused after the conversation. 1% of all those conversations amounts to 4,000 deals lost per year that you could have won. What I mean by that is if an A player had been talking to the same exact customer, your company could have won that customer's business. Multiply that by your average deal size for your company. In a transactional inside sales model, that might be $10,000 per deal. That's $40 million in missed growth opportunity per year due to low quality conversations between your company's sales team and your company's customers. This is what I mean by low quality versus high quality. So this is a real example from one of our customers. A players in green, C players in red. Both of them are trying to explain the exact same thing, which is online ads. So immediately you can tell visually, A player gets to the point, keeps it short, and respects the customer's time. The C player is trying to educate them on every possible feature related to online ads, which is usually not what the customer is looking for. When you go through that monologue, you'll probably be more confused than when you started the conversation with the salesperson. My point is that lost growth, the leading source of it, is due to low-quality conversations. So when we talk to CEOs, when we talk to VPs, we ask them, do you know the answers to these questions? Do you know what your salespeople are saying on the phone? Do you know the impact their conversations are having on prospective clients? Are they doing brand damage if they're cursing on the phone or angry with a customer because they didn't close the deal? Can you quantify the impact of these conversations on revenue attainment? And last, especially for a venture-backed company, can you reduce the ramp of your sales force from industry standard, which is 120 or 180 days, to something like 30 days? So where our solution comes in and where AI comes in is that we've developed a real-time playbook that learns what your A players say and delivers that as best practice in real time during conversations with customers. So we first learn what your A players are saying, applying online speech recognition, natural language processing, and dialogue management. So for example, what are the conversation starters that the A player uses? How do they qualify? How do they ask open-ended questions? How do they ask for business? How do they handle objections? How do they ask trial closes throughout the conversation to make sure you're engaged? These are all things we codify into what we call a playbook. The next step is we actually deliver that playbook in real time. So what I mean by that is online speech recognition during a 60-minute call, analyzing what both parties are saying, and providing a suggestion in real time to help move that conversation forward. And then the last piece, what we call postmortem, is analyzing every opportunity and why you lost that customer's business. In particular, what objections came up, why did you lose that business, where did the conversation go off track. So just a couple of quick screenshots. We can show you who's on the phone, where is business getting stuck in your pipeline, why are you losing deals, competitive entrants, product weaknesses, positioning that is confusing in the marketplace. For example, a customer who visits your website and says, I still don't know what you do. That's their opening line in your conversation. Pricing that makes it difficult to buy from you. These are all things that we can analyze by looking at the conversations and interactions between your company's sales team and your customers. What are your A players saying to win more business than anybody else on the team? This is like a magic question that nobody knows the answer to today. And last, at the point of conversation, which is the moment of highest impact, can we deliver a suggestion in real time to your salesperson to help them have a successful conversation with your customer? So overall, this is the business case for what we're doing. The underlying technology leverages online speech recognition, which is real-time speech recognition for conversations, as well as dialogue management. We view the entire set of conversations in your company as one big graph. The A players figured out the optimal policy to get from point A to point B. What we're really trying to do is help everybody else follow that same optimal policy. So, thanks.
Thanks, Sabrina. That was awesome. I'd love to figure out if we could do that for venture capitalists so we could refine our pitch. Thank you. Next up, Anthony Goldbloom. So he is the founder and CEO of Kaggle. I'm sure many of you have heard of that, heard of his company in the room. He's also been recognized by MIT as well as Forbes as one to watch, and we'll detect a little bit of an accent because he got to start working on macroeconomic modeling with the Reserve Bank in Australia as well as the Treasury.
Thanks a lot. If it's all right, I'm going to stand. So just before I kick off, just a quick show of hands who knows Kaggle in the room. Okay, quite a lot. All right. So I'm going to rip through the introduction to Kaggle, and I'm going to focus a little bit more on some of the use cases, some of the interesting things that we've done. Where we think where Kaggle tries to be is a little bit behind the bleeding edge of academia and ahead of industry, and so we're trying to bring solutions that are possible given the cutting edge of academia into industry. And the way we do this, we have an interesting model. So you come to Kaggle and you see all these problems listed, and this is just a sample snapshot of what our homepage looked like somewhat recently. So everything from stock market prediction to optimizing search relevance. And what a company will do is they'll put up a problem, like the ones listed here. We have a community of, I think, in a few days it's going to be 700,000, so it's really, really large, 700,000 data scientists from all over the world, and they'll select the problem that interests them. They'll download the data, and they'll upload an algorithm, and the most accurate algorithm wins prize money in exchange for the winning solution. And so you might think the mechanism we use is very simple. We use a type of machine. We primarily focus on a type of machine learning called supervised machine learning. So we give our data scientists two data sets. On the chart, you can see a training set where you have age and income, and you're trying to predict who's going to default on a loan. This is a very simple example, a credit scoring example. On the other half, we give age and income. We know who defaulted, but we withhold that information. And so people will download both data sets. They'll train on the training set, and we'll evaluate them on the test set. And each day, data scientists will come back and try and improve their algorithms. And so the fun thing about this is we can show people how they're performing on a real-time leaderboard. So this is a snapshot of a leaderboard from our website. You can see it has the score. So in this case, the lower the better. The score is a measure of error. And each day, people are coming back and they can put up to 5 submissions per day. So they're trying to improve their algorithms over the course of a couple of months. And so this has this very interesting effect. This is actually one of our very, very early successes. Was with NASA's Jet Propulsion Lab. I'm not going to explain the use case, but it was an image recognition problem. And so the first person to make a breakthrough on this problem was Martin O'Leary, who was a glaciologist at Cambridge University in the UK. Now, I had never heard of glaciology before, but apparently they use quite complex image recognition techniques. So his research was all about taking satellite images and detecting the edges of glaciers algorithmically. And it turns out that those techniques end up being very powerful on the problem that NASA put up. And so he got into first place. And to explain this chart, the y-axis is error. The lower the better. The x-axis is time. So Martin's very happy. He tells all his friends and family that he's winning this competition. Go check him out on the leaderboard. That doesn't last for very long because somebody passes him. And you can guess what happens next. Whereas if Martin was working by himself in isolation, he might have given up. But then Martin has to try more to regain the lead, and he gets into first place. And then somebody passes him, and there's iteration until the point where the competition ends. And you'll notice that the increments by which people are passing each other are getting smaller and smaller and smaller. Now, the intuition here is that for any data set, there's signal and there's noise. There's only so much information you can pull out of a data set. And so if somebody's working on a problem in isolation, they'll try a few things and then they'll stop. But the competitive pressures and the leaderboard push people to do better than they otherwise would. And so from a company perspective, companies typically use us in one of several situations. One is they have an existing algorithm. They don't know how strong it is. Insurance is a big industry for us, perhaps not surprisingly. So they want to predict who's going to crash their car, claims prediction. How good is our algorithm relative to how it could be? One of the really hot areas for us has been around image, speech, text. This is another use case. We can now, thanks to deep neural networks, we can do very powerful things with data sets that we historically couldn't do very much with. And so companies it's very hard to find people who are really good with deep neural networks, but if you want to see whether a use case is possible, putting up on Kaggle is a very quick way to get a sense for what's possible at the cutting edge of machine learning, and is it accurate enough to then implement into your company. So I'm going to some of the use cases now that we're seeing, some of the sort of interesting use cases that are leveraging modern machine learning techniques that we're seeing with some of our customers. So this is one I'm particularly proud of. We did this with Booz Allen Hamilton and the National Institute of Health. So this, you can see, is it's an MRI, and it's measuring a pumping heart. And what mostly when we are diagnosing heart failure, we use an echocardiogram. It's much cheaper than an MRI, but an MRI is far more accurate. We don't use MRIs because it's extremely laborious for a cardiologist to make a diagnosis of heart failure from an MRI. Well, it turns out that with deep neural networks, we're actually able to... It takes about 30 minutes, by the way, for a cardiologist. They draw the circle around the heart, how big it is when it's systolic and diastolic, and then measure what's called ejection fraction, the ratio of the heart when it's small to when it's big. It's a very tedious process. So it turns out that deep neural networks or convolutional neural networks, to be more specific, are able to do this, obviously not taking half an hour, as accurately as cardiologists. So we worked with State Farm, the American insurance company, and actually AXA, a French insurance company, on sort of advanced insurance use cases. So one is taking telematics, so the device, the pattern of acceleration and braking that comes from when somebody's driving a car, to figure out who's driving. Is it the son? Is it the father? Is it the spouse? Who's driving the car? And the reason that this is important is if you could use a mobile phone to be a telematics device, if you could automatically detect who's driving the car. So they call it driver fingerprinting. Turns out you can detect with 98% accuracy who's driving the car just based on the pattern of acceleration and braking. Another medical application, again, one by recurrent neural networks, so taking EEGs and figuring out whether somebody's grasping or whether they're lifting. So if you can get more accurate, you could get to the point where somebody could think and the prosthetic could move. Also with EEGs, we've done predicting seizures an hour before they happen. I'm actually going to skip ahead. So skip ahead to, we're at the University of Toronto, and the University of Toronto has been very, very successful, both from a machine learning perspective, but also on Kaggle. So this is a competition we ran for Merck to take chemical compounds to predict which drugs would make for good, which chemical compounds would make for good drugs and which ones wouldn't. And actually, Jeff Hinton, who I think will be here later today, and some of his grad students won this competition. It was the first one to be won using deep neural networks. And then the competition we launched immediately after this one was for a job advertising site called Adzuna in the UK. What they wanted to do was take the text of a job ad and give guidance to the company posting the job ad as to what the benchmark salary for that job would be. And again, deep neural networks, it was another of Jeff Hinton's grad students. It was the competition directly after that won. And after a couple of wins by deep neural networks, we started to see them really starting to take over on Kaggle. So just to end off, this is an AI conference, and I want to end this talk in perhaps a little bit more of a measured way. So we have run competitions that haven't been as successful as we would like. And this is an interesting one. We worked with the Allen Institute for Artificial Intelligence on can you train an artificial intelligence to solve an 8th grade science quiz. And the winning algorithms ended up scoring about 60% on an 8th grade science quiz, which is really not spectacular. We were certainly hoping for a stronger result. And I end off with a question that we looked at the types of questions that the top performing algorithms got right and which ones they got wrong. And so this is an example of a question that tripped up most of the submission, or a lot of the top submissions in our in the competition. So of the top 20 teams, half of them got this question right, and half of them got it wrong. So the question is: motion with accelerated speed and motion with constant speed are represented by different equations. Which of the following best describes motion with accelerated speed? Well, a decently strong 8th grade, the top 20 in a big class will absolutely get this question right. And as I said, half of the top 20 algorithms got this question right, and half of them got it wrong. And you can see the half that got it right got changes in velocity over time. The half that got it wrong got time over changes in velocity. So very exciting times for machine learning and artificial intelligence, but still a lot of work to be done before they reach their full potential. Thank you.
Yeah, so next up is Sean Gurley. He is the CEO and founder of Primer. And the other thing that's very interesting about Sean is a tool that we've used, and Siobhan in particular when she was doing her early research on the machine intelligence map, was Quid, where Sean formerly was the co-founder and CTO of. And he worked at NASA, got a PhD in physics from as an Oxford scholar, and now we're going to hear the latest thoughts on machine intelligence.
Yeah, look, so today we're still very much in stealth mode. You'll hear a lot more about Primer next year. But today we're going to talk instead about spreadsheets, killer robots, and high-frequency trading, which should be just about as much fun. But we're going to talk about that because I think it starts to shine a little bit of a light on what happens when white-collar jobs get taken by machines. And to understand that, we need to go back in time to 1979, when the cutting edge of computer graphics was represented by this, and most businesses were run on these, paper ledgers. Paper ledgers were great because you could write down sales and time and add them up with a calculator and a pen and paper. And you did that because any change literally meant you had to go back and change the whole thing. But this is how businesses were run. And they were run, it kind of seems strange that we did it this way. And of course it was strange because there was a lot better way to do it. And we could actually do this. And in 1979, VisCalc came along. The first commercial spreadsheet from Dan Bricklin out of Harvard Business School creates the first commercial spreadsheet. And this was amazing because it automated a human task inside of the business environment. It added things up. And this doesn't seem like a lot. Literally, if you were sitting down to run a complex calculation like a discounted cash flow analysis on a moderately sized business, that could legitimately cost you thousands of dollars and take a couple of weeks to get done. So this was revolutionary, and I don't think we quite understand how revolutionary it was. Indeed, this kind of stuff really drove a lot of early PC sales, and the head of IBM at the time was quoted as saying that spreadsheet software was the #1 driver of computers as they moved into business. So what did this look like if you were an accountant that was formerly writing things on paper ledgers? Well, my favorite story is from an accountant in Cincinnati a guy named Don Jackson. And Don Jackson had about 40 or 50 customers. And he got this new Apple computer and a copy of VisCalc. And he'd go through and he could do, actually, in the course of 15 minutes, he could do what would have taken him a week. Really, really transformational. However, he couldn't send the results out to the customers in 15 minutes because they wouldn't believe he'd actually done the work. So he did the work in 15 minutes on the spreadsheet, put the thing on his table for 3 days, and then sent it to them and got the adoring phone calls later. Which seems kind of weird, right? But you're going from a place where it literally took thousands of dollars and hundreds of hours to the cost of electricity in a few microseconds. And this is the phase that you get when you roll out human replicating technology. It's the phase of arbitrage. The phase of arbitrage you move into. And this is a great phase, and we can't quite see that, but it seems like that's the place we think mostly. But the really thing here, there we go. The interesting thing here, what we look at, is where you go next. Because when Don Jackson in Cincinnati would put out these models, the customers would look back at them and say, well, what if we looked at it and said sales, instead of growing by 3%, grew by 5%? And what if we reduced transportation costs and pegged it to a reduction in the forward strip price for oil? Or what if Germany didn't do quite as well next year in our sales planning? So you very quickly move out of this arbitrage phase into the what-if phase. And the what-if phase is very interesting because it starts to give the seeds of new industries. And new industries came along, such as this one, and this is the rise of high-yield bonds, or as you know them better, as junk bonds, and Michael Milken creating an entire industry behind that. Now, this simply wouldn't have been possible because you couldn't calculate the forward yield curves on these complex bonds and do it across enough asset classes to actually make a reasonable business. Michael Milken did this, dominated Wall Street, and then did what everyone who dominates Wall Street does, gets put into jail. But he did this in 7 years, from the addition of the first spreadsheet that took for us from paper ledgers to creating an entire industry on Wall Street and transforming the entire space. And I think this is what we're looking at here when we think about what it means to take computers and replace white-collar jobs. You go through arbitrage, you think about, well, what if I change things, and finally a new industry emerges. So I'm going to jump from there to stock market trading, humans versus robots. And if we look at that, we want to look at the techniques they use. And we'll jump in here and take a look at robots. And a robot technique for stock market trading looks something like this. There are different strategies, but it's a very, very common one. This is pairs trading. You convert a stock price time series to a series of zeros and ones and go and look at all the other stocks and see if another thing moves along the same lines. If you do, you find it and you start looking at them to monitor if indeed they split apart. If they split apart, you sell the top one and buy the low one in the belief that it comes back together. Now, the thing here is this is a very, very simple strategy. This is not smart by any means. It doesn't take into account that one of the stocks might be Facebook and one might be Twitter. But it doesn't really care because it's doing this across thousands of things. This is a very, very simple algorithm. And if we compare that to a human might look at that and say, no, these are very different. We should treat these differently. But the human has another problem. When we look at how humans work on this, humans have this biological brain that has biological limitations. And biological limitations particularly look at this in terms of speed. And the speed of strategic thought is one of the really fundamental limits that we're not going to get past. So if you put any person who doesn't know chess and put them at a chessboard and say, is the king in checkmate, it'll take about 900 milliseconds to figure that out. If you train for 20 years, you can reduce that to 650 milliseconds. But it doesn't get any quicker. And this hardwired biological limit doesn't seem like a lot, but it changes the entirety of the game. Because while you're trying to figure out if the king is in danger, all of this has happened. And this is just one stock. And as a result of that, you're competing against algorithms that start to dominate. And they dominate not because they're smarter, they dominate because they're quicker. And so you end up in this kind of place. The industry conforms to the advantage given by one of the competitors that dominate it. And this is a neutrino-based trading platform. It's hypothetical at the moment. But it succeeds because you can find neutrinos through the Earth instead of going around them, which makes it a whole lot quicker. And so instead of competing on who's smarter, it competes on who's faster, and the entire industry looks very different. So in order to win, machines don't need to replicate human intelligence. they only need to beat us on one key variable. And if they beat us on one key variable, they dominate the industry. So this fascination with mimicking humans seems like a very, very human thing to do. It doesn't really matter because you're going to get beaten on speed or bandwidth or a combination of both. So what does it give us? Well, actually, if you stack these machines together, they actually do a pretty good job. This is the bid-ask spread from the London FTSE Exchange. And it goes down to almost zero. A very, very efficient market as it rolls out more and more algorithms. But sometimes this happens. And for those who don't read these for a living, you'll know it better as this. The flash crashed at 245, where $1 trillion is removed from the market, and we still don't quite know exactly what happened. But it brings us to the final point here, which is Wiener's law. And this is driven by automation, flying planes. Automation will routinely tidy up ordinary messes, but will occasionally create an extraordinary mess. So as we move to algorithms that are not that smart, that beat us on speed, we may get more efficient systems, but we should expect more crashes. And those crashes we may not be able to totally understand with the human brain. And I promise killer robots, but you'll have to come and see me later for that. Thank you.
Thanks, Sean. That's really very powerful. I'm excited to see what's next. As somebody who worked for the founder and CEO of VisiCorp, as well as Mike Milken, as well as now with Mike Bloomberg, I certainly have been lucky and fortunate to be in the heart of some of these changes. So very interesting framing for us. And at the end, we're bringing it home to University of Toronto, one of your own. Tomi it probably needs no introduction. He got his master's here and his MBA. And he also has sold companies to both Yahoo and Microsoft, as well as built Yahoo Answers, as well as their international search business. And one of my personal favorites is he's made the Bing algorithm and the ranking function even better through machine intelligence. So excited to hear about your latest.
Thank you. One of the things I'm really, really proud of is being one of the founding fellows of the Creative Destruction Lab. And it's amazing to see how far AJ and his staff have taken the program. All right, so I'm the... So I'm a founder of Layer 6 AI, and we're going to be talking about deep learning in the enterprise. Customers tell us that they're drowning in data. They know more about their, big companies are drowning in data. They know more about their customers than ever before, and they can describe their products in meaningful and rich ways. They use this data and a recommendation system to better serve their customers. However, recommendation systems typically only use a fraction of the available data. They look at past behavior to predict future actions, and they don't make a lot of use of the product or the customer insights they have. Deep learning lets us use all available data to make more accurate predictions. Deep learning is being used by Google, Amazon, and Netflix for their own customers. We level the playing field for everyone else. Our company is a month old, and we have amazing traction with global mass media companies and financial institutions. So this is what it looks like. Jeff Hinton would be excited. It's an end-to-end neural network. In goes everything you know, all the clicks and all the swipes, everything you know about the customers and the products, the text, the images, the audio, the video. All of that can be passed through deep learning models to create a representation. The data scientists in-house, they spend 90% of their time doing feature engineering. All of that information can go into the network to describe both the users and the items that are available. The job of the neural network is to compress all of that input into something more compact and usable to provide recommendations in real time. We take, in some cases, we take an input of over 1 million data points, and we compress that into a few hundred items. The neural network itself, it's a multi-layered network, and it uses deep learning approaches for training and for the structure. And deep learning, for those who don't know, it's modeled after the structure of the brain. It has 6 layers. The 6th layer is the integrative layer, the output. That's the name Layer 6 AI. So does this work? Well, one of our early clients was a job site. They were looking for a better way of matching applicants to job openings. And they provided us all of the previous behavioral data, so the job views and the applications. They provided us the job listings, and in many cases, the CVs of the applicants. So this is exactly the kind of data that that was helpful for us, being able to well describe the customers, the users, and the end users and the items. And indeed, our modeling resulted in a 50% improvement in the accuracy. There's a common problem called the cold start problem. So this is when a new item becomes available for sale, or when there's a new piece of media published. When nobody has interacted with it before, where do you start? How do you make a recommendation? Well, using a deep learning model end-to-end is very much like how the human brain works. We can recognize a teapot on a dining table even when it's only partially visible. And the same thing with a neural network. We train our network by, in many cases, just dropping out half of the data available input to simulate these types of scenarios. And here's a news article engagement that we did, and we beat some of the established best practices for tackling these types of problems. And the one thing that we're really, really proud of is that we architected our system to work in real time. So something like Amazon will calculate hundreds of millions of recommendations. They do that overnight, and then they serve those up the next day when you visit the site. But when you go and look at the actual products, you may see customers who bought this also bought that. It's not personalized at all to you. So we do all of that inference in real time and the training in real time. So this graph here represents a new user you knew nothing about and how the recommendations improve over time and how they beat just serving up the most popular items. So our core team has been together for 4 years, a bunch of deep learning scientists, and we publish and we talk in academic conferences, and we're looking to build a team of highly competent deep learning scientists to tackle high-value problems for enterprises. The benefits slide, I won't go through the detail, but this was a long way in the making. There's one thing about taking a MATLAB model in a scientist's computer and making that a SaaS service and serving up results with no faults in less than 50 milliseconds. And that's it.
So, another special round of applause to all these talented founders and the great applications they're building.